So hi, Margaret. Your question earlier made me think of a problem that was in my book that I thought was a little bit harder about the isotopes than maybe ones you've seen before. So I found this from my book, and it talks about gallium, which has two isotopes. And it's asking you to calculate the percent abundance of the two isotopes. I do want to remind you of one thing. When you see the number inside the periodic table, it has two meanings. AMUs refers to how much the average gallium atom weighs. You would need some conversion factor to convert that into kilograms or grams. I don't know what that is, but it's a really, really tiny unit. One AMU is about one proton and about one neutron. If you go to like 10 sig figs, there's more digits, but just to 1 sig fig, it's 1 AMU. The other thing is that the 69.723 is the grams per mole of gallium on Earth. So other planets might have different isotope distributions, but on Earth, if you take the two isotopes, you get that value. So basically, the two isotopes of gallium are called gallium 69 and gallium 71 or 71. Gallium 69 happens to weigh 68.9257 atomic mass units. A lot of times people write the letter U to mean atomic mass units. 71 gallium weighs 70.9249 atomic mass units. Now, the number that's in the periodic table is called the weighted average. And I think you know this formula, or you told me you know this formula. What that number is, the weighted average, it's the decimal abundance. Now, by the way, this question is asking for the percent abundance. So you're going to have to do a couple of things to get to the answer that they want. But the first thing you want to do is set up the equation that I think you already know how to do. So let's call the percent abundance of gallium 69, let's just call that X. And then whatever the percent abundance is of gallium 71 is going to be 1 minus X. And the reason is that the two of those have to add up to 1, right? So now remember, these are decimals. This is not percentage. The percent abundance has to add up to 100%. But if we're just doing decimals, we're going to use these values. So the overall atomic mass unit, 69.727, that's going to be some value, some decimal abundance, times 68.9257, plus 1 minus X times 70.9249. Now, the problems you've seen in your book are usually, they give you the percent abundances, you convert them to decimals, and then you're solving for one of these unknowns, or for the overall. But this one, they gave you the overall from the periodic table, and you're trying to figure out what the abundances are. So we have to do some math. 69.723, that's going to be equal to 68.9257 times X plus 70.9249 minus 70.9249X. So I'm going to put all the X's on one side and all the numbers on the other. So I will put all the X's on the, let's say, I'll keep this on the right side. So I'm going to have 70.9249 minus 68.9257 times X. And then over here, Mike, is this going to be right? I'm going to get a negative number? Oh, I'm sorry. That was a negative. So I want to put that actually on the other side. So this is going to be 70.9249 minus 69.723. And I don't have a calculator, so I have to go to the other side of the room. And I get 70.9249 minus 69.723. I get 1.2019. So basically, I forgot about this minus sign. So both of these guys got switched to the left in my mind, and then this got switched to the right, but then I wrote them backwards anyway. And then I've got 70.9249 minus 68.9257. I got 1.9992x. X is equal to 0.601, and then 1 minus x is going to be equal to 0.399. So what that means is that the gallium-69 is 60.1%. That's the gallium-69. And the gallium-71 is 39.9%. I hope this one helped. It's a little tougher, but I think you can handle it.